Okay, good morning, students. Let us start today's discussion. In the last lecture, we started to discuss about the different biasing circuits. So we have started with the fixed bias circuit. In the fixed bias circuit, we use a single voltage source BCC through two resistances RB and RC to derive voltages for emitter junction JE and collector junction JC. So a voltage appears BB across base emitter of this transistor in order to make this on or forward bias. So this is forward bias here, and the relative values of the potentials at base and collector makes this collector junction to be reverse bias. Okay. Also, we have seen that the capacitors C1 and C2 are applied here, which are called as coupling capacitors, which block the DC signals to interfere with the input or output signals. So our regime is here to look at this part of the circuitry and just assume that as if these are not present. Okay, the AC input signal and the AC output signal are not present. So in the last lecture, we also tried to look at that there are two ways. One is called as load line analysis by using the load line plot along with the transistor characteristics. We can find out the operating point. So depending on the different values of IB here, IB can be set at, of course, using the different values of RB here. So for different values of IB, we have different set of output characteristics, and for a given value of RC and BCC, we have a single equation of a at the output circuitry, which involves this path here, including the BCC, RC, and the transistor. If we write the KVL equation for this, then this results into a line like equation, which can be rewritten as here. And if we plot this particular line by calculating these values of BCE and IC corresponding to IC is equal to 0 and BCE is equal to 0 respectively, we get this particular line, and this is the line which we call as load line. So when we overlap our load line with the transistor characteristics here, then depending on the values of IB, we have a single intersect point. Suppose we take say IB1 here. So for IB1 we have this characteristic here. So intersection of load line with this characteristic gives a single point which we call a Q point or operating point, and the corresponding values of BCE is called BCE operating point or called as BCEQ, and the corresponding value of the current, which can be seen at the vertical axis, this is called as ICQ. So these are the things which we can find out. Once these are known to us, we can find out the terminal voltage, collector terminal voltage also. Now, if we change the value of RC, then we can see from this equation IC is equal to BCC upon RC. This equation that if RC is increased, then IC will decrease for a fixed value of BCC. Similarly, for a fixed value of RC, if RC is say fixed, then IC will increase as BCC is increased. Okay, so these load line we can change, okay, by changing either RC value, having R1, R2, R3 values here, or also we can change this by changing the BCC. BCC can also be changed here. So if we change BCC, BCC1, BCC2, BCC3, then we can see that the load line can be changed again. So difference one can see clearly here that how it the difference can be seen here. Any for a given value of, however, for a given value of RC or BCC, we have a single load line which correspond to the given circuit, and the intersection point gives us the operating point. So here for a circuit, we may be given the circuit values BCC, the resistances RB, RC, the transistor, and we may have to find out the current, voltages at different terminals, and so on. That is operating point. Another type of question could be like this, that we may it may be desired to have a particular value of IC, and the transistor may be given to us, and we have to design. Design means we may have to find out the RB, RC, and BCC values, or even the BCC may be given. One may have to find out the RB and RC. So those kind of problems could be there. Now let us revisit what we have done in the last lecture. We can apply the KVL in the input loop. We were having here BCC connected. Okay, BCC was connected to RC and RB like this. So it is equivalent to saying that the BCC, a BCC is connected at RB, and a BCC is also connected at RC. So separately we can separate these, okay, in two parts, and say that we take this input loop here and apply KVL into this. So current is flowing in this direction. If say the voltage between base and emitter is say known to us, if we know the type of transistor, then readily BB is known to us, or BB may also be specified in the problem. So we can assume there is some current flowing through this and then apply the KVL and rewrite the KVL to find out the current value IB. Once IB is known to us, we can find out the value of IC by just multiplying with beta value of the transistor. Okay, so IC is equal to beta times IB, and then we can write the KBL for the output loop and find out this BCE also. Once BCE is known to us, in this particular circuit, we have already said that in emitter voltage is 0 because emitter is connected with ground. So emitter is connected with ground, that's why voltage of emitter is 0. We other node voltages we can write like this. Okay, the potential difference between base and emitter we can write as the potential at base minus potential at emitter, and similarly BCE we can write as BC minus BE. So now we can find out easily the values of voltage at base and collector using these equations, knowing the values of BBE and BCE. So this is important to understand that this relation IC is equal to beta times IB is valid only in active region. So if our transistor is working in active region of operation, then this is valid. IC is equal to beta IB. However, if it is in saturation, let us revisit here. If suppose a transistor in saturation, the both the junctions are forward biased. Okay, so emitter junction as well as collector junction both are forward biased. So there is say almost equal voltage drop across these forward bias junctions. We can see here we can take here say NPN transistor. So voltage drop across this PN junction will be say of this polarity here, and voltage drop across this PN junction will be of this polarity. So we can see that the polarity of the voltage drops, they oppose each other because these are forward biased. So the however the potential drops here across the junctions are dependent on in the forward bias. Okay, when these are both forward bias, in that situation we are talking about. So these voltages are very close to say 0.7 volt, but the actual values will depend of course on the cut-in voltage of these particular junctions, and the cut-in voltages will depend on the doping levels. So uh, what we expect here that uh, emitter is heavily doped as compared to base or collector. So the voltage, cut-in voltage here say B1 and B2, then what we see that B1 will be greater than B2. So effectively if we see, then effectively the and voltage drop across this will be of this polarity, because B1 is dominating here. So, but of course, this is very close, because close to zero. If collector and emitter are identically doped, in that case it may equal to zero, but it may be very close to zero. It is now not zero, but very close to zero. So it may be zero point 0.1 or zero point 0.2 volt, like that. Okay, this is very small value, like 0.1 volt or zero point 0.2 volt. So in the circuit, we have seen that we apply a biasing voltage BCC through RC, like this, and this is here base, collector, emitter. Now, if this transistor is in saturation region, then very less voltage drop is here, almost zero. So, and the current which flows through this uh, path here, in that case, will be equal. We can write the KVL for this. Okay, minus BCC plus IC RC is equal to 0. B, if BC is also there, then we can write this, and IC can be written as BCC minus BCE upon RC. But just we talked here that BCE is uh, very small, 0. Then the maximum value of collector current, which we are going to call it now saturation current, is going to be equal to BCC upon RC. Okay, so this is the value of the saturation current. Okay, collector saturation current, which we will be getting in the case of this, because BCE is almost 0. Now we can see here why BC is 0, because both the junctions are forward biased. That's why it is very close to 0. It is not 0, but close to 0. Another biasing circuit we have is called as emitter stabilized bias circuit. So in this here we add a resistance in the emitter. In the previous case, we don't have a resistance here in the emitter. Emitter is directly grounded here. Now in this case, we add one resistance. So this addition of resistance stabilizes the biasing point of the transistor greatly. But before that, let us try to look at how we can uh, analyze this. So our circuit now is little modified here. We have the RB, RC, and one more resistance in the emitter RE here, BCC. We need to analyze the circuit. Again, for analyzing the circuit, we can follow either of the ways as we have done for the previous circuit, that we can either uh, do the load line analysis, or we can also do the analytical calculations. Okay, so in the load line analysis, again, we need the characteristics of this particular transistor. So if suppose we have the characteristics here for this transistor, then we can also write the KBL for this output loop here, which will give us the load line. And then we can do the analysis here and find out the solution. So that is always available here. Here now we will look at the analytical calculation method. So as previously we see that the current, say, through the base of this transistor is, say, IB, the current through the collector is, say, IC, and current through the emitter is, say, IE. Again, we can assume that the BCC is applied at RB and BCC is also applied at this RC separately. Okay, so we can assume that this BC, because BCC is common to both. Okay, so we can just, for the sake of understanding purpose here, we are taking the effect of this BCC separately on RB and RC. So it is like this here. BCC, we have also understand that when we say plus BCC kind of thing is there, then positive terminal of the battery is connected to that particular node here, like this. Now our job is here to analyze the input circuitry and output circuitry separately. So we can do it by writing the KVL equations for the input loop and output loops. So now it is getting clear here that the input loop consists of this BCC, then RB, and then this transistor, and this resistance. Okay, so this is BCC here, RB and RE. So this ground, both grounds are common here, so we can think that they are connected together. So now in this way, we can figure out this input loop correctly. Now, unlike the diode circuitry here, there is a difference. In the simple network, okay, we have, say, the same current flows through the through a loop here, but in this case here, because of this unique transistor which is placed here, the current through base, which is IB, and through RE, which is IE, cannot be same here. Although these IB and IE fall in the same loop here, but because of the transistor action, IB and IE are not equal. So that is the biggest difference which we can think of in analysis of this kind of circuitry. This was not obvious in the previous case because RE there was not present and emitter was directly grounded. So this problem we didn't face there, but in here, because of the presence of RE, there is a voltage drop going to happen across this resistance RE, and this voltage drop is going to depend on this emitter current IE, and IB is not equal to IE. Okay. The transistor equation, current equation IE is equal to IB plus IC will hold. Even we can say that IE plus IB plus IC equal to 0 will also hold. Okay. So the transistor current equations will hold, but no way we can assume this. Now we can very easily write the equation, KVL equation here. Just figuring out the potential drops across these different resistances RB, RE, and across the base emitter junction. So across base emitter junctions, let us say that the voltage drop is BVE. So now we can write the equation here: minus BCC plus IB times RB plus BBE plus IE times RE to be equal to 0. Now, if we look at this transistor equation, transistor current equation, I is equal to IB plus IC, and exploit that IC is equal to beta times IB, then IE can be also written as IB plus beta times IB. And we can write this as beta plus 1 times IB. So IE can also be written in terms of the IB and the transistor parameter beta factor. So this equation can be rewritten here. We can take the current terms consisting of current together. So IB, RB plus, in place of IE, we can write here beta plus 1 IB times RE to be equal to BCC minus BBE. Now from here, this IB can be taken common here, and we have RB plus beta time plus 1 times RE is equal to BCC minus BBE. Just mathematical manipulation. Now we have IB is equal to BCC minus BBE divided by RB plus beta plus 1 times RE. So we get the value of the current IB from the input circuitry in terms of the known values, the BCC, the BBE, RB. RB is known to us, beta factor is known to us, RE is known to us. The great thing which we can see here is that in the when RE was not present, okay, when RE was 0, then the current value IB was equal to BCC minus BBE upon RB. When RE is present, then we get this extra term. Beta factor we have learned, beta is very large, okay, of the order of say 100. RE is some resistance in the emitter leg. So even though if we take RE not too large, that is say if we take this of the order of kilo ohms, then we see that the effect of this is going to be 101 times RE. 101 times of 1 kilo ohm. Okay, so we can see that this RE can be used to increase the effect of the resistance, okay, the effect of this RE resistance at the input. So RE reflects as a resistance in series with RB of value beta plus 1 times RE. Okay. That's how it is stabilizes. So it is actually decreasing the value of IB by increasing the effective value of RB. Okay. So effective value of RB we can see is increased multiple times. Okay, so that is huge advantage here. So if IB is reduced here, then if we go back and see the characteristics here, then in the characteristics for small IB, we will be having some characteristic like here. Okay. Now once we know the value of this base current IB, we can again find out the other values as already we have done. Okay, we can redraw this circuit here. RC, RE, and then BCC. And of course, we have this BCC, RB. We must say that this is not two different BCCs, okay? This is a single BCC, of which effect we have just taken into two parts. Let us say that the voltage across collector and emitter is BC, and then we apply the KVL in this loop. Again, we can see that collector current is IC, whereas the current through emitter will be IE. In general, IC is also not equal to IE, okay, because IE is equal to IC plus IB. Okay, so we have an extra value here of IB into IE. That's why it is not equal. So two different values of current again flows here. But for the most of the times, people assume that IB is very small. Okay, because of this IB very small, IC is equal to sometimes IE. So this is simplification. But for exact value calculations, we have to have that. So again, if we want to do exact calculation, then IE will be written as beta plus 1 times IB, and IC is equal to beta times IB. So these are the values of the currents which directly can be found using the transistor relation when the transistor is acting in the active region. Okay, so this is valid in active region of operation. So let us write the Kvl equation here. Kvl equation we can write minus BCC plus IC times RC plus BCE plus IE times RE to be equal to 0. This is the equation of the KVL in the output loop. Now, from this, our ultimate goal is to find out this BCE. So BCE will be equal to BCC minus IC. IC we can write as, let us first write IC times RC minus IE times RE. In place of IC, we can write as beta IB RC, and in place of IE, we can write as beta plus 1 times IB into RE, BCC. So BCE is equal to BCC minus this value. Also, we can write this as BCC minus, no BCE here, beta RC plus beta plus 1 RE times IB. Okay. So BC is equal to this much. If one wants, then one can also substitute for IB here from this equation. Okay, so this value of IB can be written here. Or its numerical value already calculated can be substituted here to find out the value of the BCE. So these values which we calculate, these are nothing but operating point values of BCE, the corresponding value of IC which we have calculated will be called as ICQ. The corresponding value of IE will be called as IEQ, and this value of IB, which we are calculating, is called as operating point base current IBQ. BCEQ is further written as BCE minus BE. So to find out the collector voltage here, we need to know the emitter voltage here. But unlike the previous case, in the previous case, emitter was ground. Okay, in the previous case, it was ground, but it is now not ground. Okay, so the voltage at emitter in this case is the voltage drop occurring across the RE. So that is RE times IE. So the emitter voltage is this much. So collector voltage now can be found by using this relation. BC is equal to BC minus BE. And from here, BC can be written as BCE plus BE. Okay, so BE already found, BCE already found, then BB can find out this BC. So B is equal to IE times RE. So in this way, we can find out this. Similarly, the base voltage also can be found here, this base voltage. So we can make use of the relation BBE is equal to BB minus BE, and from here the base voltage will be equal to BBE plus BE. Okay, so these different calculations we can do in this way. So we now know all these values. The current IB we know. Okay, just we can calculate the current IB, IC, IE, the voltages at base, collector, and emitter. So everything is known to us now. This gives the operating point. Anyone having any query here? Any difficulty in understanding these? Just we are looking at that how we analyze a given circuitry, transient circuitry. Okay, so this is called as emitter stabilized bias circuit. Next, we will see as voltage divider bias circuit in the next class. We stop here. You can practice some questions based on these discussions.